All right, good morning, good afternoon, good evening, whenever you're watching this. Today's topic is going to include Chapter 9, which is inferring population means. So here, there's 6 sections devoted to this chapter on inference on population means. And today's video, we'll plan on getting on maybe the first 3 or so for our lesson today. The very first section, so the big difference here is the Greek letter. Okay, as far as before chapter 7 and chapter 8, they're all about the sample proportion and population proportion, P and P hat. So in dealing with those, the population is what we call dichotomous population, meaning, it's kind of like yes or no outcomes, success or failure outcomes. But now the outcomes are going to be a little different here, and so we're not taking an average of zeros and ones like how we did for the proportion, but now we're taking the average of just real numbers. Okay, so 9.1 we get into sample mean of random samples. So we've seen sample proportion of random samples, and we say due to the variability in our experiment, the sample mean and the sample proportion, they are random variables, right? Because for every sample that I collect, I will get a different numeric quantity. But what we say about this sample mean and sample proportion is that, well, this statistic is random, and then we call it an estimator because we're using it to estimate the Greek letters, okay, the parameters. But just as far as the inference goes, we kind of saw something similar to here when dealing with the proportion, but this is specific for the mean. So once again, we have this population. Okay, we have this population that we wish to study, and from this population, we take a random selection or a random sample, and from this sample, we record our data. So now the big difference between the proportion and the mean starts right here. So with the mean, this could be like the heights of people, the income of people, the amount of time spent on stat lab for each student. All of these are kind of numerical outcomes that could be on the real line. They could be positive, they could be negative, they could be temperature of the day, the size of the earthquake, whatever it may be. Before, for the proportion, all the outcomes here, we recorded as 0 or 1, because it's success or failure, right? Candy or toy, helper or hinderer, left or right, scissors or not, right? So the big difference here now is that what we're recording are some numbers here. So from this sample, we record the sample mean, okay, the sample mean. And from the sample mean, which is statistic, but now becomes an estimator, we use it to draw inference on the population mean, okay? So the big difference here is when we simulate, is because here we could simulate outcomes of our sample by flipping a coin or rolling a die. It was pretty intuitive in how we would simulate outcomes of this random experiment. So the difference now is, well, how do you simulate outcomes from a normal distribution or from a continuous uniform distribution? Remember that rectangle? You have to find areas in the rectangle kind of distribution, right? How do you simulate something like that? Well, I mean, you could roll a die, but it would have to have an infinite number of sides, and so pretty much as far as simulating outcomes for our experiment from our sample, it's not easy as flipping a coin, but we really rely on mathematical and probability theory to do that for us. So when we simulate, we're just going to trust StatCrunch knows what it's doing, that it was built by statisticians and is doing the right thing. Okay, but if you want to know more about how they do that, it's called probability integral transform. That's what makes these other types of simulations possible. Okay, so it kind of seems obvious here that we're using the sample mean to estimate the population mean. So the thing is that we know this is a good estimator for the population mean. Okay, and recall from chapter 7, we showed that sample proportion, P hat, is a good estimator for population proportion P. So we're going to see a lot of common themes from 7 and 8 show up again in chapter 9. So not everything is completely brand new. Okay, some ideas still remain the same. We're just dealing with the new parameter now. Okay, so for the sample mean, we know this. 1, the sample mean is unbiased when estimating the population mean. That is, on average, the sample mean is the same as the population mean. Okay, so if I were to take a bunch of different sample means, well, of course they're not going to be equal exactly to the population mean, but if I take an average of those, that would be equal to the population mean. And so the precision of the sample mean depends on the variability of the population. But the more observations we collect, the more precise the sample mean becomes. Okay, and this happened the same with the sample proportion. Remember, what is the standard error? Right, the square root of p times 1 minus p over n. Right, as n increases, the standard error will decrease. So we're talking about standard error here. Okay, so I mean, just as a reminder, what it's saying is that, look, if you're using the sample mean for a smaller sample size, right, our estimators, they're trying to hit the bullseye, right, which is the true parameter value mu. Okay, mu's right in here. That Greek letter mu is right in here. Okay, and so if we took a bunch of different samples, I mean, they will be scattered around, but on average, right, if we take the average of them, we hit the bullseye. Okay, but if we were to increase our sample size, have a very larger sample size, well, there'll still be some variation there, but we'll be much more accurate. So this is still, both of these are still unbiased, right, but this has a lot more precision once we increase the sample size. Okay, so that's what these darts are doing, and we've seen these before. Okay, and the same thing happened with the population proportion. We see as we increase the sample size, the standard error becomes smaller, and therefore we are more accurate. We have a much more precise estimator. Now, as far as simulation goes, so I want to like simulate outcomes of the sample mean. So what I'm saying is, here I have my population distribution. So what this is a rectangle, right? So that is the continuous uniform distribution, which ranges from 0 to 50 minutes. So maybe this is like the wait time. I wait for my airplane to take off, where I can wait anywhere between 0 and 50 minutes, and each time is equally likely to occur. Now, of course, this is a continuous random variable because we're dealing with time. So from this population here, I know the population mean, and I know the population standard deviation. So what StatCrunch is going to do for us, where the magic happens here, is it's going to simulate wait times for us. Simulate wait times. So down here, what you see is a histogram of 100 simulated wait times. Okay, and you can see it kind of resembles this up here. It's not going to be perfect because it's random, but it kind of resembles that. So what I did here is, for every sample of 100, I took the average of the 100 wait times and plotted it here. Okay, so what I did here is I took 1,007 samples of 100 wait times, and I took the average of each sample. So down here, this is a histogram of 1,007 sample means. And if you see here, it looks like a normal distribution, right? It looks unimodal, symmetric. And if you look here, the mean of 25 of the population, this is like mu, is about the same as the mean here, 25.03. And if you look at the standard deviation here, 14.43, and you look at standard deviation here, 1.486, is considerably less. But if we were to do this quantity here, divided by the square root of 100, which is 10, we would get pretty close to the actual. We would get pretty close to this actual number here. Okay, so let me actually open up StatCrunch to show you how I did that, and how this simulator works. Okay, so let me go to StatCrunch. Let me open StatCrunch. Okay, let me go to the applets. And let me go to sampling distributions. Okay, so here I have uniform. So my population distribution is uniform from 0 to 50. So those are like my wait times, or continuous uniforms from 0 to 50. And let me just compute here. Okay, so here it gives me this table here. Okay, so you can see here that this represents this rectangle, right, is my probability distribution curve for the continuous uniform. You can think of a wait time from 0 to 50 minutes, and each time is more or less equally likely to occur. The mean of this distribution is 25, and the standard deviation is 14.403. Okay, so this is like my theoretical model here. Previously, for proportion, our theoretical model was like a coin that we flipped, right, or a die that we rolled, or something like that. But here, it's a continuous distribution. So
from here to here is where the magic happens. So what I could do here is I can have it this. Let me just sample one time. So here I'm gonna sample. So I'm gonna observe 2 waiting times. Okay, 2 waiting times, and then with those 2 waiting times, I'm gonna compute the average. So let me just do this one time. Okay, there we go. So what this means is, okay, I observed 2 waiting times. One was like 22 minutes. One was 43 minutes. And if you take the average of the 2, you get this number here. Okay, and I can run that again. Okay, I got another 2. I took another sample of 2. Of course, I didn't get the 2 same numbers because the outcomes are random. But I get a wait time of like 25 and another wait time of like 32. You take the average of the 2, and that's what we get here. Right, and if I took another sample, right, of size 2, I get another 2, right, and I get that there, right, another average. So I could keep doing this and doing this and doing this over and over again. Like say, I could do it 5 times now. 1, 2, second sample, third sample, fourth sample, fifth sample. See, every time it does 2, it takes the average. 2, average, 2, the average. All right, so this is just a plot of all the sample means. Okay, so now what I can do is I can increase my sample size a little bit. Maybe I could do like 25 or something like that. Okay, and I can do this now. So if I do it one time, it doesn't make it rain like it did before. But these are 25 wait times. I histogrammed 25 wait times, and then I took the average. Okay, and then I took another sample of 25 and took the average. And another sample of 25 and took the average. So we're taking these random samples, right? So every time we get different outcomes, and so we get a slightly different average. But is there a pattern to this average here? All right, so let me just do it 1,000 times. Okay, there we go. All right, so what I did was I collected 1,000 samples of size 25, right? And for each of those samples, I calculated the mean. So this is a histogram of all those 1,000 sample means of 25. And if you look at it, it looks like a normal distribution. Okay. And it looks symmetric, almost the same mean, 25, 25, and standard deviation is slightly lower. Okay, but pretty neat. So I mean, I could do one more time. Let's increase my sample size to 100 now. Okay, because it's saying that sample size increases, sample mean is more precise, right? So let's run it again. Okay, let's just do 1,000 right off the bat. Okay, so I did sample size of 100. Okay, sample size of 100. And what I did was I took 1,000 sample size of 100. So I got 1,000 random samples of 100. And for each of those random samples, all those wait times, I took the average and did the histogram here. And there you can see my sample mean, it's always centered around the true mean. Okay, 24.92, this is a true mean 25. So it's always centered around there. And if you see here, the standard deviation even became smaller from the previous one. So we're seeing as sample size increases, the standard deviation of the sample mean decreases, which is really standard error. So we see it becomes more and more precise, right? More and more precise. Okay, but that's just a real nice simulation that we see here in StatCrunch. And really where the magic happens is when we simulate from here to here. Okay, it's a little bit more, we need a little bit more math in order to understand how they do that, but we'll just trust StatCrunch for now. Okay, all right. So in general, I mean, that's what we're saying. Okay, here this is distribution of the population, right? And the population has a population mean, and it has a population standard deviation. So it says if you're using the sample mean, okay, as perhaps an estimate of this true mean, well, it's going to be unbiased, right? Meaning on average, if you take the average of these sample means, you're going to get roughly 25.03, which is roughly the population mean. And also the standard error, which we'll learn, which is just really standard deviation of the population divided by root n. So in this case, if you did this divided by 10, because it's square root of 100, right? Sample size is 100, right? So it would give us a sigma over root n will give us this. So you see, as the sample size increases, this standard deviation or standard error becomes smaller. Okay. So that's just the same. Same for all populations. The sample mean is based on a random sample. Okay. So it's going to vary from sample to sample, but it is unbiased when estimated population mean. Okay, meaning that all these sample means, if you take the average of them, they're going to give you the true mean that we're after. Okay, and the standard error, which is a sigma population sigma, the standard deviation of the population over square root of n, is more more precise for larger sample sizes. That's what we just saw. Okay, so pretty much what we have here is a sampling distribution for the sample mean. Okay, just like we create a sampling distribution for the sample proportion. Okay, and here we have the mean of that sampling distribution, which is mu, and we have the standard deviation, or they call it standard error, for the sampling distribution. Right, so the standard error, what does it mean? Well, this is the typical distance we should see between the sample mean of however many observations and the true mean. So in this example here, what we have is, a student's Spotify music library has a very large number of songs. The mean length of the songs is 243 seconds, and the standard deviation is 93 seconds. Okay, the distribution of song lengths is skewed to the right. So using their smartphone, the students will create a playlist that consists of 25 randomly selected songs. Okay, so here they're kind of showing off here because they're saying that the distribution of the song lengths is skewed right. So in the previous example, the distribution of waiting times was a uniform. But when we're taking the average, we got normal. Okay, so now here they're kind of showing off. They're saying, now let's look at a distribution that's skewed. They're going to say when you take the average of those, you're going to get a normal distribution, right? So remember the population here. Okay, the population here is all the songs in the library. Okay, so and then we're going to take a random sample of 25 from that library. Okay, and so if I were to simulate, so all I did, I used that software again, and what I did is I created a skewed distribution, and I tried to get it to have the same mean as what we saw here, but of course my standard deviation is off. But I just want to show is like, let's suppose your population is skewed. So you simulate outcomes from that skewed distribution. You kind of see it here because you get a lot more outcomes here than out here. Okay, and then what if we take averages of those of 25? Okay, so what I did here was I just said, okay, let's assume the population follows some skewed to the right distribution. So let's simulate outcomes from that skewed to the right distribution. Okay, so I have these are just a bunch of different song lengths here. Okay, of 25, and then let's take the average of the 25 and plot it here. Okay, so I did this 1,000 times. Okay, so I took 1,000 random samples of size 25, right? And every time I got a different looking histogram here. Okay, for every different 25. But what I did is I took the average of the 25 every time and then plotted it down here. And if you see, I went from skewed to the right to something unimodal symmetric. It looks like a normal distribution. And if you look here, the mean here is pretty close to the mean up here, right? And of course, we're kind of getting this outcome again here. Okay, but they ask here, the questions here, it's asking, in the setup that they're giving you, the mean value of 243 minutes, is this an example of a parameter or a statistic? Okay, so a statistic always comes from the data. It always comes from our sample. Okay, the sample that we collected, right? Where the parameter, that is just the true mean. Okay, so here, this student's Spotify music library has a very large number of songs. Okay, so here it says the mean length of songs is 243 seconds. So this mean length is 243. This is a parameter. Okay, it is a parameter. Okay, and the reason it is because what they did is, they just got all of the songs in the library. Okay, all, 12,000 songs, and took the average, and this is mu. Okay, the population mean. Okay, so that's a parameter. If it were a statistic, right, it would have been like perhaps the average of the 25 selected songs, right? The average length of minutes of the 25. So it would have to come from that randomly selected sample. Okay. So parameter.
And next one says, what should the student expect the average song length to be for the playlist? Okay, well, here we're going to take the sample mean, right? We're taking the average of the 25, and so really that's just a sample mean, right? A sample mean. So therefore, since the sample mean is unbiased, the answer for number 2 is 243 seconds, right? Because we know the sample mean is centered around the population mean, right? So whether it's all the songs or just a random sample of like 25 songs, they should have the same mean. Okay, so it should be 243. Okay, now when they say what is the standard error for the mean song length of 25 songs, well, it's almost 93. Okay, almost 93, right? But it's, remember, standard error is standard error of the population. Right, it's standard error of the population divided by the square root of every sample size. So in this case, our standard error would be 93 divided by, well, the square root of 25 is 5. Okay, so that would be our new standard error. So one thing that we learn is that in looking at the behavior of the average length of time, the average varies less than the individual, right? The average song time varies less than individual song time, because whenever we're looking at the standard error for the sample mean, right, it's always going to be smaller because we're dividing by this sample size here. Okay, all right, so that's just the gist of this sampling distribution for the sample mean, and it's very similar work with what we did with the sample proportion. Okay, the only thing here is this simulating machine here. Okay, that we just have to trust this here. Next up will be a central limit theorem for sample means.